Humans have always tried to understand the physical world. More than 2,300 years ago, the ancient Greeks made discoveries that continue to shape modern scientific thinking. But discoveries in physics during the last 400 years have revolutionized our understanding of the universe. Perhaps the most remarkable characteristic of physics is that some of its greatest insights came from attempts to understand the simplest everyday events. Our understanding of the solar system, stars, galaxies, and beyond was the result of trying to understand why objects fall. Aristotle was one of the greatest ancient Greek thinkers. He believed that heavy objects fell to Earth faster than lighter objects, that if a stone and a feather are dropped at the same time, the stone will hit the ground first. This belief was accepted as fact for almost 2,000 years, until, in the early 17th century, an Italian scientist named Galileo wondered if Aristotle's theory held true. Legend has it that an assistant climbed to the top of the Tower of Pisa and dropped 2 stones with different weights. Galileo stayed on the ground to observe what happened. He watched both stones hit the ground at exactly the same time. Whether Galileo actually had stones dropped from the tower or not, he tested his idea with experimentation and observation, a process that is fundamental to science. For this reason alone, he is often called the father of modern science. Galileo calculated important information about falling bodies. He determined that as objects fall, the speed at which they fall changes at a constant rate. At the end of the first second, this speed is 9.8 meters per second. The next second, the rate of the falling object doubles. So the rate of acceleration, or change in velocity, per unit of time is a constant 9.8 meters per second per second. Galileo reduced his observations to the mathematical formula V equals gt, or change in velocity equals acceleration multiplied by time. Galileo's explanation of the speed of falling bodies was a remarkable achievement, but one important element was missing. He did not know how to explain the force that was making this happen. His use of mathematical formula to express his ideas was significant. Mathematics is the major analytical tool of physics. Almost all concepts in physics are expressed as formulas, like this one, V equals gt. The scientist Johannes Kepler, working around the time of Galileo, used mathematics to calculate the orbits of the planets around the Sun. He discovered that their orbits were elliptical, not circular, and he devised a detailed set of laws that described the behavior of the planets. By the middle of the 17th century, the work of Galileo, Kepler, and others had set the stage for the greatest scientist of the day, Sir Isaac Newton. His work has come to be called the first revolution in physics. Like Galileo's, Newton's work resulted from trying to explain common events. Did you know? In 1609, Galileo put magnifying lenses together and invented the first astronomical telescope. Using this new instrument, he was the first person to observe sunspots, 4 of Jupiter's moons, and Saturn.
Sir Isaac Newton used Galileo's work to create 3 laws of motion. Today, these laws are applied to everything from building bridges, to exploring the Titanic, to reaching outer space. Newton built on the work of Galileo and Kepler. He concluded that the motion of falling bodies, the movement of planets, and the movement of any object at any time was acted on by a force, either a push or a pull. His work is known as the laws of motion. Newton's first law states that an object's natural tendency is to continue what it is doing. If an object is moving in a straight line at a constant speed, it will continue in a straight line unless acted on by an outside force. It also states that an object at rest will remain at rest unless an outside force moves it. This is known as the principle of inertia. The first law has many examples. The space probe Pioneer 10 has been drifting through space for 35 years because no other force has acted on it. A hockey puck will continue sliding on the ice until it hits the wall, and this stationary steel pipe won't move until the excavator lifts it. An object's mass is a measure of its inertia. The greater the mass of an object, like the shuttle, the harder it is to move or change its direction. Physicists talk about mass, or the total quantity of an object's matter, rather than weight, because in space all objects are weightless, but they never lose their mass. The second law describes how an object accelerates or changes its motion when a force is applied to it. The change depends on the magnitude of the net force, or the combination of all the forces acting on it. This law also states that the acceleration from a specific force always moves in the direction of that force. The mass of the object is important too. The larger the mass, the greater the force needed to make it change its motion. The second law is written as F equals ma. This formula states that net force, or F, equals mass times acceleration, ma. This formula describes the motion of objects under most circumstances. If a ball is thrown horizontally, it will continue forever unless a force acts on it. The Earth's gravity is a force that pulls on the ball, which falls to the ground while it continues traveling horizontally. Newton's third law of motion involves interacting forces. It states that for every action, there is an equal and opposite reaction. The force of gases from the jet engines pushing on the ground causes the shuttle and the jet engines to be pushed away from the ground. Physicists use the term force to describe anything that can affect the movement of an object. For example, a person paddling a canoe across a lake provides one force, but there will also be others. The wind against the hull of a canoe, the waves, and the current. Together, these forces combine to make the net force acting on the canoe. A force has direction and magnitude, or strength. Forces are represented by vectors, such as this one. In this example, there is a force from X to A and a second force from X to B. The two forces combine to make the net force X to C. Friction is a force parallel to the contacting surface between objects. Friction between the tires and the runway will bring the shuttle to a stop. When laws in physics are expressed, outside forces, such as friction, are often ignored. Galileo ignored the influence of air resistance on the dropping stones. Newton may have ignored the influence of friction. However, even when friction is not ignored, Newton's laws still hold because they refer to net force. Sir Isaac Newton made many contributions to physics, but perhaps the most important was his explanation of gravity, one of the fundamental forces in the universe. One story goes that he got the idea of gravitational forces when he saw an apple fall from a tree. Newton was the first to understand that gravity was a universal force that influenced all objects, and that this force accounted for a variety of phenomena, from apples falling to Earth to the behavior of planets. Newton's second law of motion says, in part, that an object changes its motion when a force is applied to it. But if that force works on an apple at the top of a tall tree, could it also work on distant objects? If so, why doesn't the moon fall to Earth? The Earth's gravitational force pulls on the moon just enough to change the moon's direction of travel. But the Earth is a sphere, and its curvature is such that the moon never gets closer and stays in its orbit. Newton provided the explanation that eluded Galileo. He showed why objects on Earth fall down and why planets stay in orbit. Gravity. Newton's law of gravity states that the gravitational force between two objects is proportional to the quantity of their masses and inversely proportional to the square of the distance between them. To solve gravitational and other problems, Newton developed the mathematical tool known as calculus. Using calculus, Newton's followers were able to plot the motion of the planets and handle a whole new class of problems. In the 18th and 19th centuries, Newtonian physics revealed more mysteries of the universe. But in the early 20th century, physicist Albert Einstein introduced theories that pushed the limits of scientific thought. Did you know? In Einstein's equation, E equals mc squared, c refers to the constant speed of light. But light speed is only constant in a vacuum such as outer space. On Earth, light can slow down while passing through particles and objects.
Einstein had one of the greatest minds of the 20th century. He added a twist to the old laws of motion and helped explain the mysterious force of gravity. Top scholars continue to debate his theories, but his legacy is timeless. Einstein was a revolutionary thinker, and his theory of general relativity brought a new understanding to the concept of gravity. Einstein introduced the idea of a four-dimensional universe. The three dimensions of space are length, width, and height. Time is the fourth dimension. This idea is called the space-time continuum, one of the strangest and most difficult concepts to understand in modern physics. Einstein theorized that the mass of an object actually distorts space-time, much like the line vectors in this drawing. In his theory, planets orbit around the sun because they are moving through the distortions of space-time that have been created by the mass of the sun. Einstein published his theory of general relativity in 1915. At that time, it was believed that light had no mass and was unaffected by gravity. Einstein's theory predicted that light is influenced by the distortion of space-time. During a solar eclipse in 1919, a group of astronomers observed light from a distant star, which was normally obscured by the sun's bright rays. The star appeared to have shifted from its regularly charted position. It seemed that the light from the star had bent as it skimmed close to the sun. This confirmed Einstein's theory that the light rays simply follow the curvature of space-time caused by the mass of the sun. Although Einstein's description of gravity is very different from Newton's, the two give almost identical results for the weak interactions of gravity at long distances. But for strong interactions, such as predicting the orbit of Mercury, the planet closest to the sun, Einstein's theory is more accurate. Einstein believed that the forces found in nature, which are gravity, electromagnetism, and strong and weak nuclear forces, are all aspects of the same force. To this day, physicists are trying to integrate these forces into one unified theory to deepen their understanding of the universe. No one has been successful yet, but physics has come a long way since Galileo made his discoveries.
Kennedy Space Center, Cape Canaveral, Florida, January 16, 2003. On Launchpad 39A, Columbia, the first shuttle to fly in space, awaits its 28th liftoff. 7 astronauts have spent months training for this day. Eager to begin their marathon scientific research mission in space, the crew, led by Commander Rick Husband, is ready to go.
Thank you very much. Good morning, Jeff. Good luck and Godspeed.
We have a go for auto sequence start. Columbia's onboard computers have primary control of all the vehicle's critical functions. 10, 9, 8, 7. We have a go for main engine start. 5, 3, 2, 1. We have booster ignition and liftoff of Space Shuttle Columbia with a multitude of national and international space research experiments.
At 10:39 a.m., Columbia and her crew tear through the clear blue morning sky.
Columbia now rolling on to the proper azimuth for a 39-degree inclination to orbit. Shuttle on a heads-down, wings level.
In a span of just 8.5 minutes, Columbia burns 4 million pounds of fuel and reaches its orbit, nearly 200 miles above the Earth's surface. On board are Commander Rick Husband, pilot Willie McCool, mission specialists Dave Brown, Kalpana Chawla, and Laurel Clark. Also taking part in the mission are payload commander Mike Anderson and payload specialist Ilan Ramon of the Israeli Space Agency. Over the next 2 weeks, they work 24 hours a day in 2 alternating shifts. They carry out an unprecedented 80 experiments, all dedicated to research in physical, life, and space sciences. The mission is an overwhelming success. On the morning of February 1st, it is time to bring Columbia and her crew home. As the shuttle passes over the Indian Ocean, the team at Mission Control in Houston gives the go for re-entry. Columbia begins its controlled free fall back to Earth, hurtling toward the planet at 18,000 miles per hour. As it slams into the Earth's dense atmosphere, the shuttle is enveloped in a cocoon of fiery gas that burns 1/3 as hot as the surface of the sun. There is nothing to suggest that in a few minutes, this powerful force of nature will claim the lives of all 7 on board.
This is amazing. It's really getting really bright out there. Yeah, you definitely don't want to be outside now.
Columbia makes its way over the California coastline. All systems appear normal.
There it is.
Right there. There it is.
There's 7 people in that thing.
Touchdown at the Kennedy Space Center in Florida is less than 25 minutes away. Then something goes wrong. Witnesses see what appears to be debris falling from the shuttle. Mission Control is unaware of any problems, but several minutes later they notice unusual temperature readings coming from sensors in Columbia's left side landing gear. They contact Commander Rick Husband.
And Columbia, Houston, we see your tire pressure messages and we did not copy your last.
Roger,
Then, there is silence. The unthinkable has happened. Columbia has disintegrated in the skies over Texas. There would be no survivors. Immediately following the tragedy, investigators begin scouring thousands of square miles along Columbia's flight path. They hope pieces of debris that have fallen to the Earth in a shower of hot metal will provide clues. But finding answers will take months. Early indications suggest the brutal conditions of re-entry have played a major role in the accident.
The entry is a very complex problem because it has to do with taking a vehicle out of orbit going 25,800 feet per second and basically taking it to a 0 velocity. It will stop on the ground.
Hello, Apollo 11, Houston, how did it go, over?
The potential for catastrophe during re-entry has plagued engineers and scientists since the dawn of manned space flight. By the early 1970s, When the last Apollo astronauts had fallen safely through the atmosphere surrounded by fire, it seemed the difficulties had been pretty well mastered. Man had conquered the moon, and NASA engineers were asking, what next? Their answer was to build a reusable space vehicle, one that could serve a wide variety of users, from commercial satellite operators to scientists to the military, and one that could withstand the harsh environment of re-entry time and time again.
We wanted to build a very capable vehicle that could carry a lot of cargo into space and do it repeatedly on a routine basis. That was the underlying rationale for the space shuttle.
By 1981, after nearly a decade of political wrangling, design challenges, and engineering setbacks, NASA completes the space shuttle. Roughly the size of a DC-9 jet, the space shuttle can carry a crew of up to 10 astronauts and scientists to and from space. Its cargo bay is capable of handling 60,000 pounds of payload, enough to hold satellites, carry out scientific experiments, and serve as a platform for constructing the International Space Station. But to get any payload and a crew safely home, the shuttle cannot simply fall out of its orbit and aim for the ocean like the Apollo capsules before it. Once inside the atmosphere, it must glide thousands of miles and land on a runway. Its delta-shaped wings capable of withstanding hypersonic speeds provide the necessary lift. In the spring of 1981, the design is successfully put to the ultimate test. It takes over 2.5 million pounds of rocket fuel to push the shuttle into orbit, to allow it to reach a speed fast enough to counteract the Earth's powerful gravitational pull.
In order to stay in orbit, you have to be moving at 18,000 miles an hour. That's roughly 5 miles every second. That's fast. Once you're in orbit, there's nothing to slow you down. We turn the engines off. That's when you become weightless. There's no more acceleration. You stay at a constant velocity, constant speed, going around the Earth.
But to get home, the shuttle has to bleed off nearly all of that speed, and it has to do so without power.
All of that speed, all of that energy has to come out as drag. That is the only way that it gets taken out. If you were in a canoe and you put that paddle in straight down with the blade, perpendicular to the boat, you feel a force and it slows your canoe down very fast. That's drag. Same kind of thing with the shuttle.
The difference is that the shuttle is moving through the atmosphere at 25 times the speed of sound. Hitting air molecules at that speed creates tremendous amounts of friction and superheated gas.
During re-entry, you are moving through the atmosphere at thousands of feet per second. You're at hypersonic velocity. The gas outside the shuttle is at a temperature of thousands of degrees, so it's hitting the shuttle like a blowtorch.
For the crew inside the glowing space shuttle, the light show is dazzling.
Is that us that's glowing like that? Yeah. Wow, wow, wow. They're spectacular.
Though spectacular to look at, the nearly 3,000 degrees superheated air is potentially lethal. To get home, the shuttle relies on gravity to pull it toward the atmosphere. But to leave its orbit and begin the descent to Earth, the shuttle has to first slow down, and not by much.
in order to change our orbit enough so that the lower part of the orbit intersects the atmosphere, we only have to slow down by a few 100 feet per second. So that's, it's a percent. It's really a very small change in total energy. But that makes all the difference, because once your orbit intersects the atmosphere, now you start to run into lots of air molecules, and they create a lot of friction, and they're going to start slowing you down in a hurry.
Before falling toward the atmosphere, the crew positions the shuttle upside down and turns it tail first into the direction of its orbit. Then, the Shuttle Orbital Maneuvering System, or OMS rockets, begin to fire. In a few minutes, the 6,000 pounds of thrust generated from each engine slows the orbiter down enough to rip it from its orbit. Now it begins its descent. The clock is ticking, and there is no turning back.
And the first part of the deorbit is what we call this free fall trajectory. You're still weightless, but you are getting closer to the Earth. And during that time, you have to get the shuttle in the right orientation so that when you do start to get deeper into the atmosphere, you'll be able to fly.
Deciding when and where to begin the deorbit burn is an exact science. When the shuttle eventually reaches the atmosphere, it must hit a narrow corridor that will put it on a path toward the runway.
Not only does the runway have to be in front of the vehicle, but it has to happen with a certain sense of timing, because you can't be too far away from the landing site or too close to the landing site.
If the shuttle enters the atmosphere too close to the runway, the steep angle will cause it to heat up too quickly from friction, and it will disintegrate. If it enters the atmosphere at too shallow an angle, the wings will begin to generate lift, and the shuttle will skip off the atmosphere, like a rock skipping across a pond. To fall on a precise course, the autopilot steers the orbiter by using 38 small rockets called the Reaction Control System. Located in the nose and tail sections of the shuttle, these rockets fire in quick bursts and in any necessary direction. Maneuvering the vehicle requires only 25 pounds of thrust.
Sounds pretty small, but in space there's no friction to stop the shuttle from moving around, so a 25-pound rocket does the trick.
Engineers design each re-entry so that once the vehicle hits the atmosphere, it is about 5,000 miles away from the landing site. But maintaining a precise trajectory while falling toward the Earth is only part of the challenge of re-entry. The shuttle must bleed off nearly all of its speed, and it must do so at a precise rate.
One of the critical things to realize about a shuttle re-entering is that it's a glider. It has no power. So you start your re-entry with a certain amount of energy, a certain velocity. You've got to use that energy to get you to the runway. If you don't have enough energy, you're going to land short. If you get to the runway and you have too much energy, you're going to be going too fast for a safe landing. So energy management is absolutely critical.
If you have a big glider that flies just a little bit better than a brick, which is what the shuttle does, and you are aiming straight ahead to the runway and you have just enough altitude to trade for energy to get to that runway, then you probably don't have any margin for error.
The unpowered orbiter must generate enough lift under its wings to enable it to glide about 5,000 miles to a landing site. It must also generate just enough drag so it can slow down from Mach 25 to a few hundred miles an hour without getting too hot from the friction. Using the data gathered from the wind tunnel tests, engineers find that to achieve this delicate balance, the shuttle's nose has to be pitched up at a 40-degree angle as it enters the atmosphere. By re-entering at a 40-degree angle of attack, the shuttle hits the atmosphere belly first. Soon after, it is engulfed in a blanket of fire.
Basically what's happening is you're coming in so fast that a shock wave forms. It's like the bow wave in front of a ship, but magnified probably 10,000 times. The molecules of the air press in on each other closer and closer, denser and denser until they cannot get out of the way.
The heat generated from all of that friction rips the air molecules apart. All that remains is plasma, or a collection of charged particles enveloping the shuttle. Temperatures along parts of the surface reach nearly 3,000 degrees Fahrenheit. But the shock wave itself, which flows just a few feet above the shuttle, burns much hotter.
It's the same temperature as the surface of the sun. It's just an absolutely spectacular visual experience to look out and see this shock wave and, you know, realize this incredible amount of energy that's surrounding you. And you're sitting here inside this meteorite that's flying through the atmosphere coming down to Earth.
We don't want to conduct any of that heat back into the structure. We actually want to radiate it out again. We reject the heat is what we want to do. Keep it away from the vehicle.
That requires a thermal protection system capable of withstanding heat up to 3,000 degrees. For the space shuttle, the materials must also be reusable, which they had never been before. For the space shuttle, the answer is ceramic tiles made of silica fibers derived from sand. The silica fibers are mixed with water and other materials and shaped into soft blocks. After the excess water is squeezed out, the mixture is bonded in a heating process. The result is a porous ceramic material comprised mostly of air voids and the lightweight heat-resistant silica fibers. Individual tiles are cut from the large block and machined into specific size and shape, depending on which area of the shuttle they are protecting. Each piece is baked at 2,300 degrees Fahrenheit. The tiles dissipate heat from the surface so efficiently they can be held just seconds after being removed from the furnace. The tiles that will protect the bottom of the shuttle from the heat of re-entry are additionally coated on the top and sides with a black glass-based liquid. Black efficiently radiates heat, while the coating keeps the plasma particles from sticking to the tile's surface. But the tiles can damage easily.
If you take your finger and you hit a tile with it pretty hard, you can actually crack it. So they are fragile, they're brittle, they're soft on the inside, kind of like styrofoam.
In all, it takes more than 20,000 tiles to protect the space shuttle. Each one is individually bonded by hand to the surface with a rubber-based adhesive. These black tiles are capable of protecting the shuttle from heat that can reach 2,300 degrees. But a few areas of the shuttle get even hotter.
The shuttle is moving forward, and so the forwardmost parts of the shuttle actually come into contact with the air first, and they are heated hotter than any other parts of the shuttle. And that's the very tip of the nose of the shuttle and the leading edges of the wings.
Temperatures in these areas reach nearly 3,000 degrees Fahrenheit. Ceramic tiles exposed to that kind of heat would simply disintegrate. Engineers developed a non-porous composite material called RCC, or reinforced carbon-carbon. Distinguishable by their gray color, these larger and stronger pieces can tolerate temperatures much higher than the black tiles.
It's not like a tile. It's not a porous material. It's a very hard material. It's much stronger than tiles and much tougher, much more impact resistant.
The drawback is that it's much heavier, so you wouldn't want to cover the entire shuttle with it or else you'd never get off the ground. So its use is restricted to the hottest parts of the shuttle during re-entry.
In critical areas like the wing's leading edges, large round panels of RCC are fitted together. T-seals, also made of RCC materials, are used as gap fillers between the panels. Behind them, insulation materials are the final barrier, keeping the heat from reaching the aluminum wing. The thermal protection system is pushed to its limits soon after the shuttle enters the atmosphere. The friction and heat reach peak levels as the shuttle falls from an altitude of 400,000 to 200,000 feet. It is also in this region where the shuttle transitions from a spacecraft to more of a conventional airplane. As the air becomes denser, the wing flaps and rudder become effective. By using the air to maneuver like a plane, the shuttle is able to bleed off additional speed. It begins a series of maneuvers called S-turns. With its nose still pitched up at a 40-degree angle, the shuttle banks hard to one side. The lift provided by the air under the delta wings takes the orbiter hundreds of miles outside its flight path.
The S-turns bleed off energy because you're flying a longer distance to get to the runway. So you trade that energy for distance down toward the runway. We're flying a longer distance, you can take excess energy out.
Ready to go, so we're going to proceed. MTD.
Using the combination of its wings, rudder, and the reaction control system, the shuttle continues these turns, banking back and forth around the center line of the runway. Performing these maneuvers at hypersonic speed while maintaining a precise course requires vigilance and constant adjustments.
The airflow in a perfect world would be the same over both wings, but of course in the real world it never is. There are always little upsets, a little roughness in the tile, a little disturbance in the atmosphere, and you have a little upset.
15 gusts to 19, that's
Upsets that can affect the orbiter's ability to maintain a level flight path. To correct for any disturbances, the shuttle relies on sophisticated computers. 40 times a second, it calculates drag, velocity, angle of attack, and altitude. If the orbiter deviates even slightly, the system will adjust the wing flaps or fire the reaction control jets to keep itself on course. As the shuttle nears the landing site and slows to subsonic speed, the 40-degree angle of attack is ramped way down, but energy management remains critical. Engineers and researchers again turn to wind tunnel tests to find the appropriate angle necessary to land. They find that if the shuttle's angle of attack is reduced to 0 degrees, the same angle as landing a commercial jet, the airflow does not create enough drag. The shuttle would hit the runway with too much speed. It would either overshoot the landing site completely or crunch its landing gear at touchdown. But too high an angle also has potentially lethal consequences. The weight created by the shuttle from an increased angle would slow the vehicle down too quickly. The shuttle's wings would cease to generate lift. It would fall from the sky well before reaching the runway. But if the shuttle's nose is pitched up to a 14-degree angle as it slows from hypersonic speed, the balance between lift and drag will carry it safely to the runway. Since the vehicle has no power, it cannot abort a landing or be diverted to another airstrip. It has only one shot to get it right. 60 miles from the runway, terminal area entry management begins, and about halfway to landing, the commander takes over the flight from the computer.
What we've found over the years is in the hypersonic regime, the computer can actually control to a finer level than people can. As we get lower and get ready to land, we find that the opposite occurs, and the human being actually does a better job on final approach.
Less than an hour after the deorbit burn, the space shuttle and her crew have traveled halfway around the world. The shuttle has slowed from 25 times the speed of sound to just a few hundred miles an hour, landing precisely at a predetermined location. It is a site that has been repeated 111 times since 1981. But when the Space Shuttle Columbia made that familiar journey on February 1st, 2003, something somewhere along that path went terribly wrong. During re-entry, the crew inside the space shuttle hurtles through the atmosphere at 5 miles a second, surrounded by a blanket of fire. Safely reaching the runway seems an impossible feat. But a shuttle had never been lost during re-entry until the morning of February 1st, 2003. Columbia and the 7 astronauts on board raced toward the landing site at the Kennedy Space Center in Florida. But around 9 o'clock a.m. Eastern Standard Time, disaster strikes. While traveling at more than 13,000 miles per hour, Columbia, NASA's first shuttle to fly in space, shatters in the Texas sky. Thousands of searchers scour the American Southwest looking for debris. NASA officials meticulously reconstruct every moment of Columbia's mission. Analysis of the shuttle's launch 2 weeks earlier on January 16th reveals a clue. Video shows that 82 seconds after liftoff, a piece of foam 24 inches long and 15 inches wide falls from the external fuel tank. The debris strikes the left underside of Columbia. It appears to hit near the RCC panels on the wing's leading edge, the panels that protect the shuttle's aluminum frame from the heat of re-entry. Engineers are aware of the debris striking the orbiter the day after the launch, but foam debris often falls from the external tank during liftoff. It has never caused serious damage, and this time appears to be no different. The 154-foot external tank holds over 1.5 million pounds of super-chilled fuel. On the tank's exterior, orange insulating foam helps maintain the cool temperatures. Sometimes, voids can form within the foam after it is applied, trapping air or moisture inside. During a launch, as the shuttle's speed and altitude increase, the temperatures along the tank's exterior fluctuate. The trapped molecules inside the voids expand, causing the foam to crack and fall away. Investigators may never know to what extent the foam debris contributed to Columbia's demise, but one thing seems certain. The thermal protection system on the shuttle's left wing was critically damaged prior to re-entry. Satellite radar taken the day after launch supports the theory. After Columbia performs a routine maneuver, satellites detect something unusual. An object roughly the size of a notebook floating away from the shuttle. Investigators theorize it could be a piece of Columbia's left wing, a piece damaged the day before by the falling foam debris. No one at the time is aware of the possible significance of the radar data. If it is in fact a piece of the shuttle, Columbia will re-enter the atmosphere with a hole in its left wing, its crew completely unaware. On Saturday, February 1st, Mission Control prepares to bring the crew home. At 8:15 a.m. Eastern Standard Time, the shuttle's OMS rockets begin firing. 2 minutes and 38 seconds later, the shuttle begins its scheduled hour-long freefall back to Earth. Traveling at around 18,000 miles an hour, the shuttle's onboard computer steers the vehicle toward the narrow corridor that will guide it to the runway. The nose is pitched up to 40 degrees. As the shuttle passes 395,000 feet above Hawaii, it intersects the Earth's atmosphere and begins to heat up. Inside Columbia, the re-entry proceeds according to plan. The 4 crew members seated on the flight deck marvel at the light show.
This is amazing. It's really getting really bright out there.
But outside, trouble has already started. At 8:48:39 a.m., sensor readings located behind one of the RCC panels on the left wing indicate abnormal heating. But the information is contained only in Columbia's onboard flight data recorder. No one will be aware of the temperature increases until the recorder is recovered near Hemphill, Texas, several weeks later. The temperature increase is consistent with plasma gas entering a gap in the shuttle's left wing. Approaching the California coastline, Columbia begins a series of scheduled S-turns to help bleed off additional speed. The shuttle is now in a region of peak heating, the gap in its wing likely widening. At Mission Control, computers detect minimal temperature increases in the left main gear brake line, but they are not abnormal enough to suggest an impending disaster. As the shuttle tears through the western skies, witnesses capture an ominous sight. Fiery debris is falling from the shuttle. The 7 astronauts inside are likely unaware that the shuttle is coming apart. As the plasma gas penetrates further, it is probable that the wing's aluminum frame begins to warp. The wing starts to lose its aerodynamic shape. Tiles and other materials come unglued. Still, Columbia's control jets keep the shuttle on course. Over New Mexico, the vehicle banks to the left as scheduled. By now, the plasma gas reaches the landing gear wheel well on the left side. Columbia loses tire pressure. Alarms begin to sound. Mission Control contacts Commander Rick Husband.
And Columbia, Houston, we see your tire pressure messages and we did not copy your last.
Roger.
All communication is lost. According to recovery data less than a minute later, the reaction control jets lose the battle to keep Columbia and her crew aloft. The board investigating the Columbia accident issued preliminary recommendations. First, on all future missions, an on-orbit imaging of the shuttle should take place. Such detailed images taken by satellites or from the ground should reveal any critical damage before it is too late. The board also recommends that NASA implement a comprehensive plan to better inspect the thermal protection system before and after each mission. Scientists and engineers continue to develop new and stronger materials to protect the shuttle and future vehicles from the harsh conditions of space flight. As the future of the shuttle program continues to unfold, the accomplishments of the past 22 years will not go unnoticed.
Spin down at 1926.33.
It's a firm handshake with Mr. Hubble's telescope.